So right in front of this, I'm going to go into a bit more detail about electrophilic addition. Okay, because the question is about electrophilic addition and its mechanism. And remember, the syllabus is kind of specific now. It only asks for the electrophilic addition of it's only asking for the mechanism for bromination, but the other ones are kind of the same. Now, bromination was simple. That bromination, you had double bond and bromine is added. If you add it at room temperature, or the solution would be either aqueous or it would be an inert solvent, and two Brs will get added to the double bond over here. So wherever you see a double bond, bromines are going to get added. So the mechanism is like this. The first thing is we need to understand what the term electrophilic means. What's an electrophile? So an electrophile, alkenes always have electrophilic reactions. So the term electrophile is, does anyone have any idea what an electrophile is? Anyone?
It's an atom with a lone pair.
It's an atom. No. An electrophile, firstly, it's a species that is, it could be anything. It's a species that is attracted to electrons. Or you can say it's attracted to negative charge. So that, broadly speaking, is an electrophile. But not only is it attracted to electrons, it can react with them and it can accept a pair of electrons. It can accept a pair of electrons.
So doesn't that mean it's positively charged?
Could be. I mean, there are lots of options, like what type of species could this be? So anything that's attracted to electrons. So let's say there's a bunch of electrons over here. And remember, it could accept a pair of electrons. So if there's a bunch of electrons, and this particular species is not only attracted to those electrons, but it's going to gain those electrons. It's going to accept a pair of electrons. So this species, let's call that X. This thing could either be, it could be positive, right? I mean, that's one option. That's why it's getting attracted to electrons. It could also be slight positive. Even something slightly positive would also be attracted to electrons. Or it could be something that could be electron deficient altogether. So these are all the options. That it could be a positive ion. It could be a slight positive atom. Or it could be something that is electron deficient. Like its outer shell is not complete, even though it's not. I mean, look at an oxygen atom. Is it an electrophile? Because oxygen has a total of 6 electrons, and it's very electronegative. So if it sees 2 electrons, it's going to be attracted to those 2 electrons, right? So an oxygen atom can act as an electrophile even though it's a neutral atom. Is that clear?
Yes.
Yes, sir.
So that's what an electrophile is. Then you have the type of reaction. It's an addition reaction. In addition reactions, what happens is that things get added. No byproducts are produced. So that's the type of reaction. It's an addition reaction. So you usually have 2-3 types of reactions. You have substitution, you've got addition. We'll do each one of them, but this one is an addition reaction. So just what the name states, I mean, you can tell a reaction is an addition reaction if 2 things simply get added. So let's say there's A and there is B, and they simply get added and they form a single molecule C. No other thing is produced. So that is addition. Then there's some other terms that need to be used, there is a term called heterolytic. Okay, let's discuss all the terms. So that's electrophile. There's another term called a nucleophile. So a nucleophile, I'm going to write next to it. Although we'll not be using the term nucleophile over here. Now, a nucleophile is the opposite. It's the exact opposite of an electrophile. A nucleophile is a species that is attracted to positive charge. So it's a species that is it's attracted to positive charge. Or we can, so it's attracted to positive charge, or we can say that it's attracted to the nucleus. And not only is it attracted to positive charge, but it can also donate a pair of electrons. So the scenario in this case would be, let's say you have X and let's take Y, and there is X. X is let's say a positive ion. So Y has these spare electrons, and they're attracted to positive charge. Now this Y could be a negative ion. It could be slightly negative. It could be a pi electron cloud. What else? It could be something that has lone pairs. Like anything that has spare electrons and it's attracted to positive charge. Is that clear? So any species, just keep it simple, any species that is attracted to positive charge. Is that clear?
Yes.
Yes.
Yeah.
And then there's another thing called a free radical. So what's a free radical? A free radical is something that that has, usually it is neutral, but I mean, it's not a necessity. It's simply a species that has unpaired electrons. So it's got unpaired electrons. What that basically means is that when it's got unpaired electrons, it's very reactive. Basically, what that means is that its bonds are not complete. Like if you look at the electronic configuration of a Cl atom, if I write the electronic configuration of the entire Cl atom, it's 1s2, and then it's 2s2, then 2p6. Then I have 3s2, 3p5, so which is 3px, 3py, and 3pz, and it's 2, 2, and 1. So what this means is that there's a p orbital that is unpaired. It needs electrons. So its bonds are not complete. It needs to bond with something. So bonds are not complete. So that is what a free radical is. And the way you denote free radicals is you denote free radicals with a dot. I mean, that dot could be anywhere around it. It just shows that the bonds are not complete. So for example, if I have Cl, I'm going to write Cl as this thing. If I have CH3, CH3 would be written as this. The OH could be a free radical if the oxygen bonds are not complete, right? I mean, it should have been H2O. This should have been CH4. There's one bond missing. There should have been, I mean, there should be something next to it. It should either be HCl or NaCl or something. So its bonds are not complete. Is that clear?
Yes, sir.
Yes, sir.
So that's what a free radical is. The way you're going to represent nucleophiles is nucleophiles are usually written with 2 dots. Nucleophiles are something that they have too many electrons. I mean, they could have a negative charge, but a nucleophile has spare electrons. That's why it's attracted to positive charges. And then you have electrophiles. You don't write anything with that because they're the ones that are going to receive electrons. So if there's an electrophile, it would just be X. So you've got C substances, electrophiles, nucleophiles, free radical. The types of reaction. Let's talk about the types of reaction. There's an addition reaction. Then there is another reaction which is substitution. So what happens in a substitution reaction? So in a substitution reaction, what happens is things get substituted. So for example, if I have NH, like we did the substitution of photochemical substitution of methane. So if I have this thing, what will happen is that the CH4 so the CH4 will, one of the H will get substituted. So it will become Cl plus HCl is formed. So the hydrogen is getting substituted with what? With Cl. And the third one is an elimination reaction. So elimination is, now elimination is this one. Just 1 second. So you've got a molecule is going to be produced in elimination. So for example, a molecule will be eliminated. So the OH and H get removed, and the carbons, they end up making a double bond. And a water molecule is produced. So a small molecule gets produced. So you've got addition, substitution, elimination reactions. Then there's another terminology that's got to be incorporated, and that is bond fission and curly arrows. So let's quickly talk about bond fission. Bond fission simply means how the bond is going to be broken. So this is what it's going to look like. There's homolytic bond fission. And similarly, there is heterolytic bond fission. Homolytic is that the bond is broken equally. So the bond is broken equally. An example for that is that you have a Cl2 molecule. So you've got a Cl2 molecule, and the bond breaks. So one electron goes back to one Cl, one electron goes back to the other Cl, and the bond is breaking equally. So that results in the formation of two radicals, because the Cl bonds are now not complete. It's got unpaired electrons. And simultaneously, you've got another one, which is heterolytic bond fission. Now, heterolytic bond fission is when the bond breaks unequally. So this is when if you have an HCl molecule. So if I've got an HCl molecule, what will happen is that if the bond breaks, you got 2 electrons, and both the electrons, they go to Cl. Now that in that scenario, that will result in the formation of ions, which is that the H is going to lose electrons and the Cl would end up with both electrons. So this is how it's going to result in the formation of ions. So very quickly, when you hear the term homolytic bond fission, the bond is breaking equally. It's splitting up. The electrons, one electron goes to one Cl, the other electron goes to the other Cl. So the electrons, both atoms, they divide the electrons equally. That's homolytic bond fission. Heterolytic is when the bonds are broken unequally. Both electrons go to one atom, and that usually results in the formation of ions. Is this clear?
Yes.
Sir.
Yes.
Okay, so right now just terminologies. We've got electrophiles, something that is attracted to electrons, anything that's attracted to electrons. We've got nucleophiles, anything that's attracted to positive charge. We've got free radicals, which have incomplete bonds. Should have been CH4, but at the moment it's CH3, so it's looking for one bond. They're very reactive. You've got 3 types of reactions. You've got addition, you've got substitution, and you've got elimination. So they're basically 3 types of reactions. Things get added, that's addition. Something gets substituted, that's a substitution reaction. If something gets eliminated from a molecule, that's a so addition is like the opposite of elimination. Now we're going to talk about, so let me bring this over here because we haven't even started talking about or discussing the mechanism of the reaction, which was electrophilic addition. So let's start talking about that now. And just give me 1 second. Now this one, electrophilic addition mechanism. And we will discuss how alkenes undergo addition. So I've got an ethene molecule. The basic reaction is when you have an ethene molecule, the bromines simply get added to the 2 carbon atoms. So nothing complicated, it's just bromines getting added at RTP to the 2 double bonded carbon atoms. So one bromine gets added over here and the other bromine gets added to this carbon atom. First thing, what is the type of hybridization when carbon is making a double bond? Is it sp2, sp3? What is it?
sp2.
sp2.
Okay, this is sp2. Okay, the carbon looks like this. It's making 3 bonds, 3 normal bonds. So 1 bond with H, 1 bond with H, and there's 1 bond with the other carbon atom, right? So carbon in sp2 hybridized carbon atom, it makes so this is sp2, both of them are sp2, both of them are identical. So carbon is making 3 bonds, and one of the orbital is available for pi bonding, or one of the electron is available for pi bonding. So that is what the carbon atom would look like. So both carbon atoms are identical, so they would be exactly the same. So this other one would also be sp2 hybridized, and these two would come together, they would bond in the middle, and they would end up forming a sigma bond. So this carbon over here, so two H atoms, and there's an H atom, and in the middle there's going to be a pi bond. So they're going to overlap, they're going to attract each other's electrons, and the electron density would be maximum in this middle area over here, and that's R. So that's our pi bond. Is that clear?
Yes.
Yes, sir.
Yes.
So what's the problem with pi bonds, and why does it attract bromine? So first thing is pi bonds have high charge density. There's a lot of electrons over here. So this pi bond over here, or the pi electron cloud that we have, let me write so the pi electron cloud that you have has very high charge density. And it's got very strong polarizing power. So it's very strongly polarizing. I'm going to explain what that means. So basically, when you have a double bond, you've got a lot of electrons in the middle. You've got a double bond, so that means there's a sigma bond that's right in the middle, and then there is, on top of that, there's a pi bond. So first thing, so there's a lot of electrons. If there's a lot of electrons, which substance will get attracted to it? Electrophiles, nucleophiles, or free radicals? But if you
Electrophiles.
TK, so it's going to be electrophiles, because anything that's attracted to electrons is an electrophile. So it attracts electrophiles. Electrophiles are attracted to electrons. Now, in our case, we have a bromine molecule. So there's a bromine molecule that's coming in. Is the bromine molecule polar or non-polar?
Non-polar.
So it's non-polar. That means the electrons are right in the middle. So it should not act as an electrophile, right? Because it's a non-polar molecule. So the thing is, it should not be attracted to electrons. Is that clear as well? Like, it should not act as an electrophile. Is this clear?
Yes.
Yes, sir.
But what happens is, what is polarizing power? That means that there's so many electrons over here. There's a pi electron cloud plus there's a sigma bond. That the electrons in bromine, if the bromine molecule is mixed with an alkene, the electrons over here are going to repel the electrons in the bromine bond. So the electrons, they get pushed in the downward direction. And one of the bromine becomes slightly negative and the other bromine becomes slightly positive. Is that clear?
Yes, sir.
Yes.
So that means, so basically bromine should not have slight negative, slight positive charges, but what has happened is that the electron cloud has polarized the bromine molecule. It's pushed the electrons downwards. Now, when this happens, now the positive bromine, there's going to be heterolytic bond fission. Why? Because the negative bromine would be even more repelled by the electron cloud. There's negative charge over here. So the negative bromine would be even further repelled. So there's going to be even more repulsion. And the negative bromine will get pushed away. It will eventually break away. Is that clear?
Yes.
Yes.
Yes, sir.
And simultaneously, what will happen to the positive bromine? The positive bromine would be even more strongly attracted to the electrons. So the positive bromine will get attracted to the electrons in the pi electron cloud. Now, there's one thing I forgot to mention over here. Let me add this. When we were using the terms, there's a thing that even in the question they're going to use, and they'll tell you that you should use curly arrows or you should show curly arrows. So what are curly arrows? So I'll just quickly tell you what curly arrows are. I mean, it should not be really curly. I mean, you can probably get away with them not being curly. A curly arrow shows the movement of two electrons. That's a full curly arrow. So if there's two electrons moving from, like over here in the HCl molecule, the two electrons, they went towards Cl. So that shows the movement of two electrons. Vice versa, if you have one electron moving, so that's going to be, it's going to have a half a arrowhead. So that shows the movement of just one electron. So this one shows the movement of one electron. So you've got movement of two electrons and you've got movement of one electron. Like over here, one electron went to this Cl, so that's the movement of one electron. One electron went to this Cl, so that's the movement of one electron. So the only arrows that you show, it's the arrows represent the movement of electrons. They don't represent the movement of the atom. They don't represent the movement of the ion. Like over here, what was happening? The positive bromine is getting attracted to the pi electron cloud, right? So the positive bromine is moving in the upward direction. It's actually going, or it's getting attracted to the pi electron cloud. But I'm not going to show it with an arrow. I mean, I should not have drawn this arrow. I'll remove this later. But the direction of the arrow is from this to this, because the electrons are the ones that are getting attracted to the positive bromine. Vice versa, the positive bromine is also attracted to the electron. So, I mean, I could have drawn the arrow in the other direction, but the curly arrow represents the movement of electrons. In what direction are the electrons moving? So these electrons are getting attracted to the positive bromine. Is that clear?
Yes.
Yes.
So what happens is that the bromine got polarized, and so the story is that the bromine got polarized. One of them became positively charged and the other one became negatively charged. The negative one got even further repelled by the electron cloud. The positive one got even more attracted to the. So the next step is, here's your next step. This is what's going to happen. A carbocation is going to be formed. And let me explain what a carbocation is. So in the next step, let's assume that the bond has now finally broken. This BR, the bromines have separated. So the bonds have been broken. This bromine got both electrons. Now it's no longer slightly negative. Now it's actually a fully negative ion. It's -1 now. The other bromine lost both electrons, so it became a positive ion, right? So it basically became a +1 ion.
Yes.
So what that will do is that the positive bromine is going to take away all the pi electron cloud. So this is the next step. That what will happen is that the positive bromine is going to go. It's going to be attracted to the pi electron cloud. It's going to go, and it will start gaining the electrons in the pi electron cloud. So the double bond electrons, they would all be attracted to this positive bromine. Okay, just a second. I made all the corrections on the other one. Just 1 second. Just 1 second. Okay, this one. Just 1 second. As anyway, so let me just So anyways, you had a Br positive, you had a Br minus one. The two things, they got separated. So they eventually got separated, and yep. Now the positive bromine, I was at this point that the positive bromine is going to go, it's going to get attracted to the electron cloud, and it will try to gain those electrons. So what it will do is, the positive bromine, it's going to steal all the pi electron cloud, all of it. And it's going to take those electrons, and it will try and attract the electrons. The positive charge on the bromine will go away. Why? Because it got its electrons. The pi electron cloud, they're now with bromine. This carbon actually ended up losing electrons to bromine, because the pi electron cloud belonged to this carbon atom. I mean, what was happening was that these carbons were together having this pi electron cloud, but the pi electron cloud is now between these two things now. All the electrons over there, they got attracted to this bromine. So the other carbon became positively charged because it lost its pi electron cloud. Is that point clear? Yes,
Yes, sir. It can be between any two carbons, right?
it can be
Between any two carbons, right?
the Br, you're saying that should be on this one.
It can be also in that carbon, right?
It can be on that one, right?
Yeah.
So now the next part is this Br with its electrons, with its spare electrons.
Yeah.
It's Haji.
So, would the bond between carbon and the bromine atom, would it be a dative bond?
It's kind of a dative bond, but not really, because and here's the reason why. See, let's focus on this thing again, right? It's Br plus one, right? Let's focus on these two carbon atoms. The Br was making a pi bond with two electrons over here. So it was making a pi bond in this direction with the other carbon atom. But now all of a sudden that carbon, its pi electron cloud, the pi electron cloud was over here. It got pulled by the Br over here, right? So you're saying that it's a dative bond. Why? Because the Br is not contributing any electrons. Is that clear? I mean, that's what you're saying, right?
Yeah.
So now the thing is that it's not really going to be, the concept is exactly the same, but the reason it's not going to be a dative bond is that one of the electrons is basically, it's going to make Br a neutral atom. So it actually ends up gaining those electrons, one of the electrons, because it's a positive ion, right? So one of the electron, the Br would gain, and it would become a neutral atom. And then it would make a normal covalent bond. I mean, this is what it's going to do. Like, think of it this way. So the electron, one of the electron goes to Br. The Br no longer is a positive ion. Is that clear?
Yeah.
And then the two get together to form. So now it's like a normal covalent bond, right? The two are going to get together, and then they're going to form a normal covalent bond.
Yeah, I see.
Okay, so the point is, I mean, the concept is exactly the same as dative bonding, but it's like a covalent bond where Br first ends up gaining an electron, and then it ends up forming a covalent bond. But the basic idea is, in simple terms, what's happening is the electrons in the pi bond, they're now with Br. In the next step, you got a carbocation. This is known as a carbocation intermediate. So this is your carbocation. Intermediate. And you've got a Br minus one that was floating around. That is going to come back, and that's going to make the other bond now. So this is what happens. Polarization. Why? Because polarization, because of the pi electron cloud. One of the Br gets attracted, the other one gets repelled. The positive one gains all the pi electron cloud, bonds with one of the carbon atoms, the other one becomes a carbocation, and then the next step is the Br minus one that was floating around, that is going to join in. Now I'm going to quickly write the mechanism for what you're going to write the mechanism in your exams. So it's going to be this thing. All you have to show is, I mean, you need to know the detailed concept, but all you have to show is every curly arrow, every single thing has to be correctly drawn. So you have a Br, another Br, you're going to show the molecule getting polarized. So So that's step number 1. And when the molecule is polarized, at the same time, it would be trying to gain electrons. The positive bromine, this is slight positive. The one underneath is slight negative. So it will try to gain electrons from the pi electron cloud. So the next step is a carbocation would be formed. One of the BRs would gain electron from the pi electron cloud. It would form a carbocation. And in the next step, the Br minus 1 is going to come back. It's going to get attracted to the carbocation, resulting in the formation of the bromoalkane, which is so resulting in the formation of 2 bromines. They are going to get added to it. Is that clear?
Yes.
Yes.
So you have to learn this mechanism, and you should know that it's a proper 2-step mechanism. The middle part is known as a carbocation intermediate. Is a carbocation an electrophile? What's a carbocation? It's a molecule where the carbon has a positive charge. And whenever you use the term intermediate, what that means is that thing is actually formed in the reaction. It's a proper 2-step reaction. First, one thing forms, so that there's a step 1, and then followed by a step 2. So you could actually stop the reaction at step number 1. The intermediate, whenever you use the term intermediate, it's something that is present in the solution, and you can actually stop the reaction at that point. You can prevent it from moving further on. So there's a carbocation intermediate. It's a proper 2-step reaction. So if somebody is asking for an energy profile diagram of this reaction, we don't know whether it's exothermic or whether it's endothermic, but a proper 2-step mechanism, it's energy profile diagram. If you remember O levels you did energy profile diagrams. So energy profile diagrams for 2-step reactions would kind of look like this. That there's going to be and then there's going to be the second reaction. So this is the energy axis. We don't know which one is exo, which one is endo, but I'm just drawing a rough sketch that you'll have your reactants. So that's R. You'll have your intermediate. So you'll have your intermediate, and then you have your product. So it's a proper 2-step reaction. Is that clear?
Yes.
Actually, we're going to do it.
Sorry, sir, but what will be the conditions of this reaction?
We did the conditions earlier. We did all of these conditions. Like we did bromination, right? It's Br2 RTP, and it should be in the dark. We did hydrogenation. We did hydration. All of these are electrophilic addition reactions. Every time the reaction is kind of the same. It's with hydrogen halides, with HCl, the reaction is going to be kind of the same. So we did the conditions, the mechanism. Remember all these terms that we did? And this mechanism has to be remembered. And you need to know the concept, like who's polarizing the bromine molecule. It's the pi electron cloud that's doing that. There's heterolytic fission that's going on. I mean, you can add, this is heterolytic fission. So we're not talking about the conditions at the moment. We just want to know what the mechanism of the reaction is. With HPR, it's going to be the same. With water, it's going to be the same. Okay, with water, it's H+1 will get attracted to the electrons, and then the OH -1 from water will come in the next step. So, but you need to know the mechanism of bromination only, not about the other ones. So let's continue with this. There's another thing, we'll do that, and then we'll continue with the questions. Okay, so we'll just continue with this format. Hopefully, we'll cover the organic chemistry and we'll do more questions next time. Okay.
Sir,
Yes.
we have to go.
ठीक है, ठीक.
It's,
Chalo, let's continue next time. Okay. Allah Hafiz.
Okay, sir. Allah Hafiz.
Okay, sir. That is-